The basis for molecular interactions is often based upon the polarity of the molecule. The polarity of the molecule can be determined through the individual bond polarities and the geometry of the molecule. I'm going to show you how to determine the bond polarity and the overall polarity of the molecule based on its geometry. The first thing that you do when you see a molecule is you should draw it in 3 dimensions. So here we're going to start with methane, CH4, and I'm going to draw it in 3 dimensions. Recall that when carbon makes 4 bonds, its shape is tetrahedral. If we were to look at this as a 3-dimensional model, we would see that it is symmetrical, in that every bond has the same angle between all the other bonds. The next thing that we need to do is determine the polarity of each bond. If you look at your electronegativity chart, you'll see that carbon has an electronegativity of 2.5 and hydrogen has an electronegativity of 2.1. And the difference between their electronegativities is 0.4. That means that the sharing of electrons is going to be relatively equal. So we are going to label these as nonpolar. And because every bond here is the same, everyone is nonpolar. In addition to that, all of the hydrogens are evenly spaced around the carbon, so the overall molecule is nonpolar. Now let's look at water. I'm first going to draw the 3-dimensional shape of water. Because oxygen has 2 lone pairs, the shape is bent. On the top we have our 2 lone pairs. Those take up space and are highly negative, and they repel each other, and thus they make it into a bent shape. You can imagine that they take up shape coming forward and going back in space, much like you would see on a tetrahedral. So I could draw this slightly differently, like this. With my hydrogens in the same plane as my oxygen. And then my one set of electrons and my other set of electrons going forward and backwards in space, taking up that space. We're going to work on this first drawing here. This was just another way to look at it. When I analyze the individual bond polarities, I will find that hydrogen and oxygen is a very polar bond, with the electrons being pulled towards oxygen. Oxygen is going to get this delta negative, and each of my hydrogens partially positive, delta positive. When we're looking at the polarity of a molecule, we can draw what are called bond moment vectors. They show the direction of the negative charge. So it looks like this, with the arrow going towards the negative and the plus sign of the line going where the positive is. When I draw that for my water molecule, the plus goes at the hydrogen with the arrow going towards the oxygen. And that looks the same on the other side. And those are my bond moment vectors. To determine the overall polar moment vectors, you have to look at whether or not the bond moment vectors cancel out or whether or not they go in a general direction. Because both of my bond moment vectors on this side and on this side go towards the oxygen, the overall vector comes from this side of the molecule towards the lone pairs. These hydrogens are evenly spaced apart, so this side is overall positive and this side up here is overall negative. The overall polar moment vector will go through the top here, and that overall polar moment vector tells me that this is a polar molecule. Here's a picture showing this as a space filling where you can see the positive at the bottom near the hydrogens and the negative at the top. And so the overall polar moment vector goes straight from the bottom in between the two hydrogens up to the top. Let's look at our last one here, boron trifluoride, BF3. First, we have to look at what the Lewis dot structure is for boron. Boron only has 3 electrons surrounding it, and fluorine has 7. So the Lewis dot model looks like this. Because there's no lone pair of electrons here, this molecule is planar, trigonal planar, and it looks like this, 120 degrees between each of the bonds. If we look at our electronegativity chart, you'll see that the difference between boron and fluorine is 2, meaning all of our fluorines are going to be partially negative, and our boron is going to be partially positive. If we draw our bond moment vectors, they will go from the boron to the fluorine on all 3 sides, like that. Then you need to determine whether the overall molecule is polar or nonpolar, and this is determined by the geometry. You can see here in this geometry that each fluorine is going to be pulling equally on the electrons of boron. That means that not one side of this molecule is going to be negative or positive. Overall, this molecule is nonpolar. When you're looking at the polarity of a molecule, you're looking at overall, is there a positive side and negative side? That's what you're looking at overall. And that can be determined by the bond polarities and overall the shape. If there is an unequal pulling on one side versus the other, then the molecule is going to be polar. But in the case here of boron trifluoride, because all the fluorines are pulling equally on our boron, even though the bonds are very polar, the overall molecule is nonpolar. So you have to look at the distribution of the vectors overall and at the individual bond polarities. Let's do one from our homework. You should be able to do part 1, but for 2, let's do the first one together. Let's do A, formaldehyde. First, I need to draw the Lewis dot structure. Start with my single bonds. And I'll recognize that there are 2 lone electrons, so I'm going to move those in and make a double bond. There we go. Now I'm going to draw it in 3 dimensions. Because carbon only has 3 bonding partners and it has a double bond, it's going to be trigonal planar. Next, I'm going to determine the polarity of each bond. My carbon-hydrogen bond is nonpolar, and my carbon-oxygen bond is going to be partially positive and partially negative. Since I determined that my carbon-oxygen bond is partially positive, partially negative, I'm going to erase the nonpolar that I did in the first one. And now I'm looking for the overall polar moment vector, and that goes straight through the middle towards the oxygen here. Because the bonds with hydrogen are nonpolar, meaning that the negative charge overall for this molecule is going to be over here, and then down on this side, it's going to have its positive charge. Overall, this molecule is polar. All right, see what you can do.